Morning, students. After a long break, we are coming back to the our process control class. Now this is a class for our last this is the continuation from the last class, where we have discussed about motion balance type controller and pneumatic controllers. Just for a revision, pneumatic controllers are of two major categories: motion balance type and force balance type. Motion balance type controllers are based on the principle of movement of a motion beam, that is as shown here. Here is the motion beam, this is the motion beam, and this movement of this beam behaves like a flapper unit towards the nozzle. So with the movement of this flapper or the motion beam, the nozzle feedback pressure changes, and that behaves as a control action. And depending on type of pneumatic bellows and valve arrangements, the proportional, and integral and PID controller can be designed. And in our last class, we have discussed that motion balance type PI controller, motion balance type on-off controller, motion balance type proportional controller, and finally we discussed about PI controller. And today we will show that the PI controller of motion balance type, how this works as a motion balance type PI controller, the mathematical model, and its functionality. This is the motion beam. As you have seen that this is the motion beam and two bellows elements are there. This is for the input signal, this is the measured signal coming from the process, and this is the set point bellows through which the set or desired signal is sent. So the mid portion of this motion beam behaves like a flapper unit in front of nozzle. Now how it works, see, when the measured value, say when it is in steady state, that means measured signal and set point are same value, that means the process value is at desired value, then there is no signal change between the two bellows element. But when the measured value, say if the measured value exceeds over the set value, what will happen? At the point C, please note that this is point A, this is point B, and this is C. This point A, just a minute, this point A behaves as a this is the point where two bellows element both are behaving as a controller element. This portion is for proportional controller, and this portion acts as a integral bellows element. This is called proportional bellows, this is our feedback bellows, and this is called integral bellows or reset bellows. The point at this adjacent to this bellows element is called A. The midpoint, which behaves as a flapper, is B, and the point between this measured signal bellow and set value signal bellow is pointed as C. Then when the measured value exceeds over the set value, what will happen? The lower point C will move towards towards right. The lower point will move towards right, and at that point the point A acts as a pivot. Why? Because the signal at these two bellows element will not change instantaneously. So this point A will behave as a pivot, and this, since the measured value exceeds over the set value, so the motion beam at point C will move towards right. A acts as a pivot, so this B will move towards the nozzle direction. Then what will happen? The nozzle feedback pressure will rise. This is simply the pneumatic nozzle system, where the air supply system, I am not repeating the nozzle action, just if the flapper moves towards nozzle direction, then nozzle feedback pressure will rise, and that pressure will go to the feedback bellows element after a small time delay, and the pressure signal will move to the other side of the bellows, that is called reset bellow, through the reset restrictor. This is called reset adjuster, through the restrictor. So that will be a delayed effect than this feedback bellows. So what will happen after a small time delay? The pressure at this bellows element will exceed. This is labeled as P2 and P3. Sorry, this should be P3, P4. This is P3, P4 like. So the pressure at this bellows element will rise over this bellows element, this bellows pressure. Then what will happen? After a certain time delay, the point A will move towards left, isn't it? The point A will move towards left, and at that time C act as a pivot, because there is no further change in pressure between these two bellows elements. So at that time C act as a pivot, A will move towards left. As a result, B will also move away from the nozzle direction. So in next level, the nozzle feedback pressure will decrease. That is the effect of proportional controller. So this causes the movement of a decrease of pressure signal, and the pressure signal at this bellows element will also decrease. And after a certain time delay, through the restrictor, the pressure of this bellows element will rise above this. So in the next level, this point A will move towards right again. So now the when the pressure at this bellows element will increase, the motion beam at point A will move towards right. At that time C will act as a pivot, and B will again move towards nozzle direction. Then what will happen? The nozzle feedback pressure will rise. This is the integral effect, that is the additional effect of proportional. So this will behave as a integral action, and in this way the adjustment of control signal gradually will achieve. Now how this is the functionality, and how this can ensure that PI effect is generated. That is, we will establish the mathematical model of this PI controller. The beam movement, whatever we have discussed, that in the first level the B will move to say B1. This is due to input signal. So this is called say theta I, input signal, and at C at that time C will move towards C1. So this is say theta in dash. This is for the theta n signifies, this is for input signal, uh, the point movement, motion beam movement from B to B1 due to input signal, that's why theta I. This is the theta n dash for flapper movement towards nozzle direction. Then what will happen? The feedback bellows element pressure signal will rise. So this movement of point A to A1 may be labeled as say theta F due to feedback signal, and this as a result the C will move to new position, say C2, and this is the away from nozzle flapper movement away from the nozzle direction, say theta n 2 dash. And in the next level A will move to A2, and this is due to integral effect. So as we have considered, this is integral effect, so this may be considered as theta capital I. This is theta small I for input signal change, theta, and again this is the flapper movement towards nozzle direction. This is say theta n 3 dash. So the effective displacement is theta n equals to theta n dash minus theta n 2 dash plus theta n 3 dash. This is the effective movement of flapper towards nozzle direction for a complete motion, for 3-step complete motion. Now, so this is our equation number 1. This is written over here, that theta n dash minus theta n 2 dash plus theta n 3 dash is the effective displacement or net deflection of flapper towards nozzle direction. Now, from the figures, see, from this figure, see theta n dash by this theta I, from the principle of geometry, that this C1 by B1 is equals to AC by AB. So this is, if we can write this as, say, theta n dash, this theta n dash by theta I is equals to AC by AB, that is this theta, that is this theta n dash theta n dash is equals to AC by AB into theta I. Similarly, theta n 2 dash is equals to, from the triangle here, see, theta n 2 dash is BC by AB theta F. BC by AB, theta F and theta theta n 3 dash is equals to BC by AB into theta I. Okay, so then from the equation, this theta n dash minus theta n 2 dash plus theta n 3 dash, if we can write the net deflection theta n is equals to AC by AB theta I minus BC by AB theta F plus BC by AB to theta I, isn't it? Now from Flapper-Nozzle principle, that from Flapper-Nozzle principle, we know that the pressure P0, the output pressure P0 is proportional to the deflection. So P0 equals to say K theta n plus some constant K1. So if we put that this theta n is equals to P0 by K minus K1 by K. So this our initial equation was theta n equals to theta n dash minus theta n 2 dash plus theta n 3 dash. So now we can write from equation 1 that this theta n, that is theta n is P0 by K minus K1 by K is equals to this much AC by AB into theta I AC by AB into theta I. Since the expression is large one, so I don't want to skip the levels, plus BC by AB theta I. This theta I is for integral action deflection. Now this from this Bellows element principle, that P0 from Bellows principle, this P0 into AF is equals to KF into theta F. This is for feedback Bellows element. AF is the cross-sectional area of the Bellows element and theta F is the displacement. So theta F is P0 F by KF. Similarly, theta I This is for the integral bellows element. This will be P0, I say Ki into Ai. This is for integral bellows element. So theta f, actually we are trying to find out this theta f and theta I, which we are getting from equation 1. So next, if we put this to the equation here, say P0 k by k minus k1 by k is equals to, where theta f is P0 by kf and theta I is P0 by ki ai. So putting this here, we are getting that P0 by k minus k1 by k is equals to, okay, once again I'm writing this as AC by AB into theta I, okay, theta I minus BC by AB into theta F. Theta F is now P0 AF by KF. F by KF is constant, and plus BC by AB. Theta I is P0 by Ki into AI. So this is P0 by AI, so P0 by Ki into AI. So BC, AB, AF, KF all are constant. So P0 and here is another P0 term. So the output pressure in terms of, so from here we can write theta I P0 AI by Ki. BC by AB into P0, okay, BC by AB into, okay, once again, I'm keeping this as theta I because the change of theta I'm mentioning that this is theta I, say, this is theta I, keep this theta I as it is. So theta I equals to, just check, AB by BC into 1 by K plus BC BC by AB into F by KF. I'm writing this from this term, BC by AB, F by KF. Just taking the common term P0. Okay, AC by AB into 1 by K. This is from here. And next is BC by AB, AF by KF into P0 minus the theta I term, that is AC by AB. Just cross check the terms. AC by AB into AB by BC. This term AB by BC as multiplying this AB by BC in the both side. So AB by BC into theta I minus AB by BC that is the constant term, this one K1 by K, K1 by K. So this theta I, just all these are constant terms. So simplifying this, we can write as this theta I is equals to say K2 P0 minus K3 theta I minus another constant K4. Again, this is equals to K2 P0 minus this K3 theta I can be written as K3 another constant K5 into error signal. Since the error signal is, or the displacement, this theta I, this is due to the change in error. This is proportional to error. So this is as theta I proportional to E. We may consider this as equation number 2. So this is the expression for theta I in terms of the nozzle feedback pressure P0 and the error signal, that is the measured value difference set value in terms of measured error signal and the nozzle feedback pressure or output pressure. Now mass flow rate through the integral restrictor, which was shown here. Now this mass flow rate through this restrictor is the pressure difference, that is the output pressure. This is the pressure, this bellow pressure, as this is integral bellow, we may consider this as Pi due to integral element. This is Pi, and the nozzle feedback pressure as per our convention, this is P0, output pressure or PO. So this the mass flow rate through this integral restrictor, mass flow rate is dm dt, and that is equals to the pressure difference, that is the nozzle feedback pressure minus the integral bellows element pressure Pi by the restrictor R, that is the mass flow rate. Say this is equation number 3. So from gas laws, we from gas laws we know that the pi vi is equals to nRT. This is for integral bellow element. This pi and vi, this pi for the integral bellow element pressure and the volume vi of the integral bellow element, and this n is m by capital M into RT. This m m is, so this mass of this gas small m is equals to, from the expression, this is equals to m into pi vi by RT. By RT, and this can be written as k theta into pi plus kt into vi. This is kt, where this k theta is the constant for increase in pressure. This k theta is the constant for increase in pressure at constant volume, and kt is the constant for increase in volume at constant pressure. So this again, this vi is ai, this vi is equals to ai into theta I. Ai is the area and theta is the displacement or change movement. So vi is ai theta I. Once again repeating the significance of k theta and kt. K theta is the constant for increase in pressure at constant volume, and kt is the constant for increase in pressure at increase in volume at constant pressure. Just the reverse. So the values are, now see, this is our equation number 3, and now this is equation this is this expression for small m. This is our say equation number 4. So from equation 3 and 4, what we can get, that this P0 minus Pi by R, from equation 3 and 4, P0 minus Pi by R is equals to k theta del Pi del T. Since this is dm dt, so dm dt, so del Pi del T plus kt ai, putting vi equals to ai theta I, kt ai del theta I del t. I think this part is clear. This dm dt is k theta del pi del t and kt ai del theta I del t. So P0 minus Pi is equals to r k theta, just multiply with r k theta del pi del t plus r into kt ai del theta I del t. So this P0, so this P0 minus Pi is again Ki by Ai theta I. See, this Pi was this one. Sorry, this should be Pi, not P0. This is for integral values. So this should be Pi so this Pi is equals to Ki by Ai into theta I. So putting this here, Pi is Ki by Ai into theta I equals to R into K theta and del Pi del T. So this should be Ki by Ai del theta I del T, because the variable is the displacement. So del theta I del T plus R K T Ai del theta I del T. So this P0 is equals to Ki by Ai theta I plus R K theta Ki by Ai plus R K T Ai del theta I del T. This is the expression for P0. So extracting theta I, why we are doing this? Because we are trying to find out the final expression which establishes that this is the effect of proportional plus integral effect. So theta I uh, theta I, okay, just that part should be considered, theta I plus this R AI, this one R AI KT AI by ki, this one, theta I plus r ai by ki into, just take the common portion, k0 ki by ai. Just check that the common portion k0 ki by ai plus this kt ai del theta I del t equals to ai by ki p0, isn't it? Just this theta I plus the common portion. This is for integral Belows element displacement. This is the del theta del t, and this is the output pressure, nozzle feedback pressure. So this is exactly like theta I plus this r, and the rest portion is a constant. Maybe the capacitive part c del theta I del t equals to ai by ki p0. So this is like the desired expression, theta I plus rc d theta di dt plus the constant into p0. So theta I plus this rc is equivalent to the integral action time ti into d theta I dt equals to, this may be considered as some another constant ai by ki into p0. Now the theta I was from our previous expression, this the theta, yeah, the theta I is k2 p0 minus k3 k5 e minus k4. If we put that theta I here, then this is equals to k2 p0 minus k3 k5 into e minus k4. This is theta I plus ti, and d theta I dt is k2, just differentiating this, k2 dp0 dt minus k3 k5 d dt. d dt. Right? So the final expression is for P0. See, this is P0. So K2 minus AI by KI P0 plus K2 Ti dp0 dt equals to K3 K5. Just rewrite the expression in terms of P0 and E plus K3 K5 K3 K5 Ti d dt and another constant is plus K4. Just simplifying the equation by side changing. So the expression is dp0 dt equals to K3 K5 by K2 Ti into E plus K3 K5. All these are some another constant into d dt. So this P0 is equals to say another constant K6 integral e dt plus K7 say E. So the final expression is one for proportional and another part is for integral. So what I am trying to derive this detailed mathematical model from the motion balance type pneumatic PI controller is that principally that is equivalent to PI effect, but how or whether it is exactly establishing the PI model or not, that is why we are trying to derive the mathematical model. Now for PID controller, only one part should be incorporated along with this P and I. That means there should be a derivative restrictor and the effect should be after a delayed effect, that is due to the derivative control action. So only the model, if you draw the model of this motion balance PID controller, that is sufficient to explain, because the other steps are exactly similar. And another type of pneumatic controller is force balance type controller. Force balance type pneumatic controller uses the principle of balancing forces on certain diaphragms. Like this is the force balance type PID controller, where the chamber, this is the controller chamber where the that is separated by several diaphragms, and this is the input signal or measured signal, and this is the set point signal. So all are separated by diaphragms, several diaphragms, and chambers are A, B, C, D, and the lower one is E. The lower chamber is connected with the nozzle element, and these three successive diaphragms are connected by a pilot valve which behaves as a flapper unit towards the nozzle element. What will happen? See, if the input, I am explaining that part later. First, this chamber that is separated by into five chambers by 4 diaphragms, A, B, C, D, E, 5 chambers. C is connected with the measured signal or input signal, and D chamber is connected with the set point signal. Now, if the measured signal exceeds the set value, what will happen? The pressure of this chamber C will rises above the chambers D. So the diaphragm at this point, just a minute, the diaphragm at this point, should use this color. So the diaphragm at this point, the pressure will be more to this diaphragm, and that will act downward direction. So this pilot valve will move towards nozzle direction, and nozzle feedback pressure will rise as a result. Then what will happen? The nozzle feedback pressure is directly connected with this chamber. So the and connected with the upper two chambers through the restrictors RP and RI. This is for proportional effect, this is for integral effect. So what will happen? This is directly connected with this. So the chamber pressure will rise. Then the chamber pressure will rise means the pressure on the diaphragm to the upward direction will increase. So the pilot valve will again move away from the nozzle direction. So the nozzle feedback pressure will fall. So this is the effect of controller, that whenever the pressure will increase, in order to adjust that will finally decrease the controller output pressure. So the nozzle feedback pressure will decrease, and after a certain time delay through this restrictor, this pressure chamber will rise. Then what will happen? Again the pressure of this diaphragm towards the downward direction will rise. So again the pilot valve will move towards this direction, and after a certain time delay, the pressure at this chamber A will rise. So when the pressure at this chamber will rise, the diaphragm will move downward for this separation AB. The diaphragm between AB will move downward direction. As a result, the pressure of this chamber will rise. So this will cause the increase of or movement of pilot valve towards nozzle direction. So nozzle feedback pressure will rise. Only if you analyze the diaphragm, or if you can remember the diaphragm, then you can analyze the action. Now after this PI effect, the signal will move to another chamber where two diaphragms will separate the chamber into three portions, F, G and H. Again, as this pressure will increase, then the pilot valve will move towards the nozzle direction and the nozzle feedback pressure will rise, but derivative action is just the reverse effect. Then what will happen? The this signal is connected through the restrictor and it is connected with the mid portion. Then the mid portion chamber pressure will rise. Now see, the lower pressure signal remains constant. So the pressure signal of this chamber will compare with the upper signal, as this is enclosed one, the lower one. So the signal pressure signal will be compared to the diaphragm here, and that will if this pressure at G increases over F, then it will move upward direction, the diaphragm will move upward direction. As a result, the pilot valve will move away from the nozzle direction, so the nozzle feedback pressure will decrease. So finally, the output from this is the relay unit. So output from the flapper nozzle unit and pneumatic relay is from the output from this relay unit is the PID control action. So this is the force balance type pneumatic controller. That's all about pneumatic control systems. In next class, I will discuss about the electronic controllers. Okay.